Welcome back, y'all. So today we're going to be talking about peptides. And so what I mean by peptides is really just a bunch of chains of amino acids. But for every peptide, there's always two ends. It's always a linear type of molecule where there's always one end, which we call the N terminus right over here. Usually has the ammonium ion on one side, and then the other side has a carboxylate anion. So in this case, the C terminus. And so by convention, every time we write out the three-letter codes, right? So if we say GLY, ALA, right? Or leucine, isoleucine, glycine, right? Every time we draw those and list those amino acids, we always have it with the N terminus, the amino acids on the N terminus on the left side, and the amino acids with the C terminus on the right side. Now, this type of linearity is very important. So, for example, like glycine alanine, so this molecule right here, is completely different than alanine glycine. Despite them using the same two amino acids, because the direction is reversed, they are two different molecules. So in this case, looking at this first molecule right here, first we have glycine first, right, with an R group of H. And so this would be glycine. Then after this peptide bond, so the C-double bond O to NH, we have a CH3 right over here. And again, look, this is the N terminus with the ammonium ion right here, and the C terminus at the very end, right here. And then because we have our R group right here with alanine, this is our molecule, glycine alanine. However, if we look onto this side, if we notice here's the N terminus, here's the C terminus, the closest to the N terminus in this case now is alanine. And then on this case, since the group here is an H, we call that glycine. And so there's a linear difference between these two, especially with the N terminus and C terminus. Now, when we talk about the peptide bond, there's actually a lot of important properties to it. So, for example, looking over here, let's say we have alanine valine, right? So this CH to two CH3s and then a CH3 right here. This peptide bond is actually an sp2, meaning it's planar in some sense. But it also has two different conformations. So in this case, trans, and the other case, cis. Where the trans conformation is more stable simply because the two R groups are on the other side. And then cis would be less stable because both R groups are on the same side, lost their kindreds. But the point is that these are both planar because this can resonate between the N and to the C-double bond O. And that's important in terms of backbone structure when we're talking about peptides. Now, in this case, there is one specific reaction that you might need to know for this class. Now, it's called the Edman degradation, and the point that you should keep in mind about this entire mechanism is that it is an N-terminus removal, meaning that it removes amino acids one at a time starting from the N-terminus. Well, what do I mean by that? Well, what I mean is, okay, so every time, let's say we had some three-letter code right over here, right? So asparagine, glutamine, and leucine, right? And then in this case, I'll talk about this reaction a bit later. When we do the Edman degradation, so we call this the Edman degradation. First, we get a molecule of ASN, PTH. And again, we'll talk about this later, but it essentially cuts off this N-terminus amino acid and then leaves just the last two, in this case, glutamine and leucine. All right, but how does this reaction work? Well, the first step in this reaction is this. We have to go to the N-terminus, right? And again, assuming we don't have the ammonium, it's just an NH2. First, we take these electrons, attack the C, move these up to the S right here. So that does a nucleophilic attack. Okay, so then from that, we make this crazy ring. Again, just keep in mind of all the different things that we've done. Take the S electrons, attack to this C-double bond O, and then we can just move these bonds onto that NH right here. Now, what that does for us is what we call a nucleophilic acyl substitution, meaning that we can take we can add this S to the C double bond O and then kick off whatever was on it. So in this case, what we do is kick off that NH group, or this NH2, and this is our glutamine leucine in the previous step, right? So this is like the rest of our molecule. But again, for now, what we're going to be talking about is just that this is the rest of the amino acid chain. But up here, we still have some rest of this crazy molecule right here. Now, after we add some H plus and some heat, we get this rearrangement, and we get this 5-membered ring with a phenyl group at the very end. But what you should notice is that there is this R group right here, right? So this specific molecule is what we call phenyl thiohydantoin, or a PTH. And that's why in this case down here, we drew PTH-ASA, right? Now this R group will change depending on that amino acid that was right next to it. So in this case, we had PTH-ASN, so we would draw our molecule looking like this, NH2 and to some R group, and I'll just draw the rest of the 5-membered ring first, and just to make sure I'm not kidding myself. All right, and then here's the phenyl group, so benzene ring, you know, some crazy thing right here. Now, remember, this R group will change depending on what amino acid we did, right? So in this case, we had asparagine, and so the R group for asparagine is a CH2 to C double bond O and H2 right here. And so this is what PTH ASN would look like. But remember, this bond right here will change depending on what your R group is or your amino acid that you put in. But just keep that in mind when you're doing that reaction. Okay, now this is just more of a skill that I believe that it might be extremely useful to you in the future as well for this class. And so really, it's just practicing reading long chains of peptides. So in this case, my method, at least, that I like to do is first I want to find the N-terminus, right? Now, it sounds easier than it looks, right? Because there will be a lot of NH2s in your molecule, but what you need to know is you need to find really the N-terminus. So first you need to find a lone NH2 group, right? Okay, so let's say we find that lone NH2. Okay, let's look right here. Now, one carbon over will have an R group, right? Okay, so that R group can be anything from glycine to alanine to, you know, a bunch of other things, right? But the point is that it has to be an R group, not a C double bond O, just a single sp3 R group, or the next carbon over. 2 carbons over, right? So this is a 1, this is 2. 2 carbons over will be a C double bond O. That's how you can tell whether the NH2 that you chose is an N-terminus, right? And so next C has an R group, and then 2 C's over equals a C double bond O. Okay, now after we find the NH2 group, then we can try and start following the backbone. And so it will always have, so the pattern of the backbone is always NCC. So N-terminus to a chiral carbon into some kind of C double bond O. Okay, so and then carbons between the peptide bonds. So in this case, you know, let's say we had, this is part of the peptide bond, this is part of the peptide bond, this one right here, will have the R groups. So let's put this into actual practice, right? So here's what we call copper peptide. This is a type of hormone that's released into your body. Now, okay, how can we apply what we've learned, right? Okay, well, in this case, there are 2 NH2 groups that are shown, right? So we could have a lot of different possibilities, but let's look at this first one down here, right? Okay, so, okay, we have this NH2, go 1 carbon over. Okay, there might be an R group, might be CH, right? And, you know, the R group for glycine is just an H, so that doesn't really tell us anything. Let's go 2 carbons over. Well, the problem is this second carbon right here, that's not C double bond O. So that can't be the NH2 for the N-terminus. Okay, so if that can't be the NH2, then well, let's look at the other one. Well, okay, so this NH2 right here, okay, go 1 carbon over. Again, might be an H. Remember, glycine is perfectly fine. Go to the next carbon over. Oh, that's a C double bond O. Okay, all right. Well, in this case, this is probably our N-terminus right here, right? Okay, so now look at the backbone, right? So NCC, NCC, NCC. The last C on this case, the C double bond O, we can tell that can be the C terminus. All right. But now we need to find all the different R groups, because then we can tell the different amino acid chains. Okay, so starting at the NH2, right? One carbon over, well, that must be an H. Okay, so the R group for that case, that's going to be glycine. Okay, now this right here is going to be peptide bond, right? C double bond O to an NH. So, we don't care about that. We can just not skip it, but we can move on to the next carbon after that peptide bond. And what we get is this one right here. Now we get this imidazole group right here, and the imidazole group, well, we like to call that histidine right here. Okay, so we're almost done. Now, one peptide bond over, right? C double bond O to an NH. And then our next molecule, or next R group right here, is going to be a CH2 to CH2, 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 NH2. Well, this long chain with an amine group at the end, we like to call that lysine. And then we have a C terminus. So this linear chain, if we were to list out all of its 3-letter codes, we call it lysine, histidine, lysine, in this specific order. And so this is, again, a practice, and if you look at my worksheet that's on the Google Drive, we have more examples on there. But this is how you would at least read amino acids.